Electromagnetic Induction Lab, Physics 124, SUNY, Fredonia, Professor Alan Haungs. Basic concept number two. We're going to talk about Faraday's law of induction. Our last lecture that preceded this, we touched on what is an electromagnet. And the reason we did that is so that you would understand that magnetism not only comes from a permanent magnet, but can also be made from an electrical device that uses electricity, and that a moving charge causes a magnetic field. Now we're going to be talking about induction. Now we used that word induction in a previous lab when we were talking about induction in the electrostatics lab, where we were able to take an electric field, expose something to an electric field, and cause a polarization to occur within an object in which some of the charges would move to one side of the object and then others, the opposite charge would be on the other side of the object. So we would literally cause a displacement, a redistribution of charge within something. We induced it. And we could cause actual currents, electrical currents, to flow just by using an electric field. Here we're going to use magnetism to also cause a similar effect, and that we're going to literally cause charge to move via a magnetic field. It works differently, though, with a magnetism than it does with a static electrostatic field. Electrostatic field can charges are actually literally attracted to an electrostatic field or repelled. Not in the case of magnetism. That's the mystery. So we're going to explain how is this possible that you can displace charge with something that neither is attractive to nor repulsive to charge. Okay, so this is where it gets extraordinary. There's a guy named Michael Faraday, and he was not a very respected person during his life, at least not initially. He didn't come from a wealthy background. And he was a person who came upon how magnetism could be used to induce a voltage in a wire. So let me just demonstrate something to you first. Piece of wire. Okay. It's hooked up to my oscilloscope. That's this device in the back. That line represents a voltage. So if it goes up, it means it's a positive voltage. If it goes down, it means it's a negative voltage. If I were to take a magnet, okay, that is the, that's the northern, so northern force is coming off this magnet. You've probably seen pictures of this. So you picture arrows jumping off the end of this magnetic field coming off of this magnet. If I were to just take this and just swipe it by the wire, you see the wire, you see the oscilloscope moves. Okay? So what just happened was, when I took this North Pole and I swiped down, I create a positive voltage. Conventional current flowed this way. I create a positive voltage. Conventional current flowed this way on the wire. If I swipe it up, I create a negative voltage, and I had conventional current flowing this way in the wire. Now, how is that even possible? It's possible because a changing magnetic field, a changing in intensity magnetic field, creates an electric field. And that the electric field that's created, its magnitude is proportional to the rate of change of the magnetic field's intensity. So in the space that this wire is occupying, that space is experiencing a change in magnetic field. And this wire is harvesting the effect of the electric field by creating a voltage on the end of the wires. Now, the other bizarre thing is that this electric field always occurs at right angles to this electric field. So if I got like little arrows sticking out of here, out of this North Pole, the electric field is always at a right angle. So when I swipe it back and forth like this, what I'm doing is I'm creating an electric field that runs parallel to this wire, and that wire then responds by having a voltage there. What if I were to increase the magnetic field by going like this, just going in and out like this? Well, that does not create a voltage on the wire. Why not? Did you say that it creates an electric field? It did. This time, though, as it's increasing, the electric field is not running parallel to the wire. It's running in a circular fashion in the wire, or in the space that the wire is occupying. So what happens is as much force is going this way on an electron, some are going this way. So you may have displaced electrons that way. You may have displaced, so that the ultimate thing is you've displaced them equal amount in opposite directions. You have nothing. So that's why you don't see any voltage when you do that. But if I wanted to harvest the electricity from that magnet by going in and out like that, well, if I just turn this into a circle, then it would work. Then it would work. See? Now it works. Now it works. See? Because the electric field now is in this direction, it looks like it comes around like this. I'm not creating a straight line electric field. I'm creating a circular one. Okay? Now Faraday didn't have sensitive equipment like I have. So he had to use something more like a coil of wire, because you would never, with the equipment he had at his disposal, you could never get enough voltage or current and a magnetic field strong enough to see this as well as I just did. So what he did is he created something of this equivalence. This is something I made. It's just two coils that are wrapped around one magnetic core. The magnetic core, what it does is it creates a very high conductive path for the magnetic field. So if I were to apply current to this coil here, that magnetic field will travel through this core, and then this magnetic field will also experience almost the exact same amount of magnetism that this magnetic field had actually emanated. Most of it stays inside this core. So he arranged a situation in which he then electrified an electromagnet. So this will be our electromagnet. And then he had another coil on the other side that he was just observing, what does this coil do? So what would you expect to happen if I were to just pass a DC current through that coil? Well, I can do that. Well, let's attach this to our oscilloscope. Okay. Here we go. I'll attach this to our oscilloscope, and I'll just pass a DC current through this coil, and see what happens. There we go. I'm right now passing a DC current through there. I'm passing a DC current through this right now. And the voltage on this side, passing a DC current through here, the voltage on this side measured by the oscilloscope is nothing. So nothing happens. But what would occur if I could change the amount of current going into that electromagnet? Let's say if I just increased the current, what would happen? Oh my goodness, look at this. We see a voltage on that other side. So if I were to, I'll show you. So right now I'm going to increase the current. Watch. When I increase the current, I got a positive voltage. I'm holding it the same current. Now I'm going to decrease it. I got a negative one. I'm still holding the same current. I'm going to increase it. Went up. I'm going to decrease it. Went down. So If I could have smoothly transitioned it into perpetuity, constantly increasing the current through that coil, you would have seen a steady voltage here. Or if I could have perpetually decreased it, or then decreasing it to zero, then transition and then flip the polarity around and continue to go down, you would have seen a steady voltage here. But I can't do that. I can't. My equipment won't let me go up to infinity. So, but if I could, that's what you would see. Um, and so, um, this is extraordinary. So this is called induction. We're inducing electricity in this secondary coil. We'll call this our primary coil because we're putting power in from this side. This is our secondary coil or our pickup coil because we're receiving an effect. This is why it's called induction. These two coils are not touching each other at all. There's no electrical connection here. This, by the way, is the precursor to what we call an electrical transformer. If you were to have a transformer that converts, like on the telephone pole, if you were to convert the 7,000 volts on an electric pole to the 120 volts you use, it'd be something that looks just like this inside that little canister that's hanging on the pole. It's just an iron core with some wires wrapped around it on one side and then other wires wrapped around the other, and there would be a ratio between these two sets of wires, and I'll explain that to you in a later video. And a transformer works by electromagnetic induction. So we use electromagnetic induction every day of our lives, whether you understood that or not, whether you realized it or not. Michael Faraday's experiment and his observation was groundbreaking.